Kiddos, here's where we were yesterday, right? Yeah, that's good. They can all go on top. Yeah, there you go. Hey, guys. Time for class. Okay, so notes open. We were here yesterday. Yesterday we saw, first of all, beginning of section 5.2, we saw that sometimes when you solve differential equations, you end up with y stuff on the left side and x stuff on the right side. That's the only legal way to rearrange stuff. And then we integrate both sides, kind of like implicit. We would derive both sides. We integrate both sides. There's some things where we could be writing lots and lots and lots of different plus c's with different subscripts, but eventually they kind of just all get absorbed. But sometimes the c gets stuck, and you have to leave it there. You can't go pulling it out. Sometimes the c gets stuck when we solve for y. And then we said, hey, there are these special differential equations. Now that you've kind of seen what a harder one looks like, there are these special differential equations where the rate of change is directly proportional to the original amount. Or the rate of change is proportional to the original amount. So change is directly proportional to the original amount. Every time this little differential equation is going to end up with the same result. Now, if you have something extra going on, like divided by x, or something extra going on, like now there's a y squared, maybe some things will change. But these are two very common differential equations that always result in what we would call exponential growth. And we're going to, when we get to a word problem, talk about how all these different variables behave and how we can kind of assign values to them. And some of you guys that have talked about or learned half-lives or doubling before, maybe you'll see where that whole ln equation came from for the constant, for the rate of change. Okay, so then coming back. We did not get to fill in this one, and guys, we're not going to do all the work because we did it once. Can you guys at least realize that it'd be very, 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 very similar? We would still divide by y. We would still end up with an ln. We would still take e to both sides. We would still do the snazzy thing with the plus c to make it a constant times c in the front. All that would be different, so I'm going to do a dot, dot, dot with a little choo, 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 dot, dot, dot. You'd end up with y, and technically you can put it y of t. You don't have to put it y by itself. Would be c e to the negative kt. Now technically, if you just see k as a constant, k could be positive or negative, so I guess it's a little redundant to put the positive or negative, but it's just showing you that when you have growth, that k is going to be a positive number, and when you have decay, that k is going to be a negative number. Now, we're not going to go into word problems right away. We're still going to camp out just for a little bit longer on, hey, differential equations are a little trickier. Remember I said in past years that there would be a handout that would go along with this section because the book was more laid out like a college textbook. Like in college calculus classes, normally you wouldn't, in like the first level of calculus, you wouldn't have even learned the derivatives of e or ln. You wouldn't have even talked about logarithms or, I think, inverse trig. Because they're like, you know what, those are really more complicated concepts called transcendental functions, and they would leave that for a future branch or a future level of calculus. So AP Calculus takes kind of like the beginning levels of all these different topics, it's just laid out a little bit differently than college courses. Anyway, long story short, this is an AP book, so it's like, no, you need this, so we'll cover it next. So then anyway, this whole handout thing, you guys aren't getting a handout, you don't have a homework handout. We're just using their examples because they're good ones. How would you start solving this differential equation? You can't add because you wouldn't get the bookend, but you should divide. Now some of you are like, well, we just need the y to the other side. Don't do it, but check it out. If I added the y to the other side, wouldn't I get y plus dy dx? That's not a bookend. I need it multiplied. Does that make sense? Okay, so then that's a really bad idea. So if I can't add it, the only thing I can do is divide. The question, am I just going to divide by y? No. So if I'm dividing, I'm going to divide by?
4 minus
exactly. The 4 is stuck with the y. Sadly, it is what it is. Division, remember multiplication of a reciprocal is probably a lot easier to think of it like that. Oh, hey, most of you would actually think of, what would you have thought of doing first probably? I know a lot of you started talking about the y, but Well, if you multiply by 1 over dy, once again, you're not going to have a bookend.
Oh, you're right.
You see what I mean? It's division, so that's not going to be good. I need the differentials always up. I need the down to go up. Yeah. So I would have dx on both sides, and once the dx gets over there, you're like, he does not belong at all. Let's divide. And then we end up with the following. We end up with 1 over 4 minus y dy is equal to 1 dx. It's not miserable. We're just getting used to moving things around. Now, section 5.3 is all about these differential equations that are trickier. So we'll see all kinds of examples. But for right now, since we did kind of have to introduce trickier differential equations to show you this exponential growth and decay and how it comes about, I thought we'd do one more just to kind of see how you guys are doing. So now is it properly laid out?
Yes.
Okay. Now it's properly laid out, so I'd say integrate both sides. Yeah.
Let's go at it.
I have a function of y's with dy, a function of x's times dx. Good. I know you guys probably see over here, this one's just going to be x plus c. Question, what you thinking about for the left? 1 over u is a great idea, but don't jump there without doing the work. So, if you want to do that, who's your u going to be?
4 minus y.
What's your du going to be? Negative. Negative 1 dy, right? Or negative dy. So then if I solve for dy, I would get negative du, right?
Yeah.
And all of that was to be able to rewrite 1 over u negative du. Some of you would have jumped to 1 over u and not realized the du said, you need a negative in there. Does that kind of make sense?
Yeah.
Okay. Then over here I still have my x plus c. Is it okay if I jump pretty fast to ln?
Yes, you may.
I'm not going to put a plus c because remember that plus c comes over and joins with, yeah. You have a few different options.
No, let's divide by
Illegal. Okay. It's illegal to take an e if there's still a negative in there. You could move it up to be a power or divide it to the other side or multiply it to the other side. Now I have positive ln equals. Are you guys okay if I do negative x plus c? Remember, that could be a C1, that's a C2. Now what?
No, that's a log base.
Now the ln's by itself. Now we can do e to the power of both sides. Remember, e to the power of this whole thing's stuck, right?
Yeah.
That's all a power of e.
Can we just think about it as bringing that c down?
Exactly.
No.
Exactly. And it's not technically that we're bringing it down, but we can...
Like it's separation and then you're
Exactly. You can say, oh, this is e to the negative x times c. It's e to the times e to the, and this whole thing gets absorbed in a constant. So yes, you can think of it as c times e to the negative x because of the properties of exponents we talked about yesterday. Ew, gross. Now what?
Well, there's not really a way to get rid of the absolute value, is there?
Could you technically, this is a bad idea, can you square both sides and it would,
No,
meaning with plus minus square root?
because this
Yeah.
has to be inside.
But like yesterday, is e to the negative x ever going to be negative?
No.
No. Is c allowed to be whatever we need him to be according to our...
Yeah.
So do I really need to worry about the absolute values if I'm going to make c whatever I need him to be anyway? That's always positive. And the c is just going to be whatever I need according to the clue. So in a way you can think of the absolute value is going to be a plus or minus, and the plus or minus, since it doesn't affect this guy, is going to be absorbed into the c. Yeah. And the c, well, it's going to be whatever I need him to be. So I can go ahead and do 4 minus y. We could go ahead and write plus or minus c, but we'll make the c whatever we need him to be. Now, quick heads up, he might be positive sometimes, he might be negative sometimes, depending on the clue. But we'll figure that out when they give us a clue.
I'm sorry, why
Go
did
ahead.
we get rid of absolute values again?
Because we could write the plus or minus. And then we can say, well, you know what? We'll make the c, because this is always positive, we'll make the c whatever we need him to be based on the clue. So in a way, we're kind of like the e to the c is just c, like the plus c1 plus c2 is another c. We can kind of just say, okay,
It's absorbed.
It's absorbed into the constant in some senses. Now I need to go ahead and subtract a 4, right? Multiply or divide by a negative, right? Maybe I shouldn't do that because that's a little messy. Let me do this. Then let me go ahead and do negative times negative y equals. Do you guys see how the negative can also get absorbed into the c? So it's going to be plus 4. So my final solution is y of x, if you wanted to write it that way, is c e to the negative x plus 4. Blech. This is technically exponential growth. No, it's not growth. What is it? Exponential decay. And how do you know it's decay? Because of the exponent. However, it's exponential decay. The initial amount, or we would say the initial population, is
Why would we insert 0? Or
is equal to c plus 4. Well, it depends. Because if you plug in 0, that whole thing is 1. So you know how we're what also contributes to the initial amount. 0 power is 1, so the c is also contributing to the initial amount. This, though, let's take away the initial amount because that's just kind of getting more complicated than we need to be. The problems that we're going to look at today are not going to have an additional plus 4 something going on. It's not going to be as complicated as this differential equation here. But you guys did a great job with this equation. Let's go ahead and growth and decay specifically, which are a little bit easier as far as differential equations than what you guys just saw. Let's go ahead and skip him for now. That's more like section 5.3. Okay, how about this guy? If they want us to, given that this is a graph of, this is kind of like old school algebra 2-ish, pre-cal-ish. If this is a graph of y of t, you see two different points, and we know that it, according to what's given, it fits this pattern, it fits exponential growth. Then kiddos, how would we go ahead and fill in the equation? Plug stuff in. So let's start with the first one, right? If we plug in 0, 4, then we would say 4 is equal to c e to the k times 0. What happens to anything to the 0? Always 1. So guess who is the value of the initial? Yeah. When t is 0, when time is 0, the 4 is seen in the c. That's a hint about exponential growth, that this place right here, this c place, is always going to be the initial amount. Now, if it's a little bit harder with like a plus something, it might change a little bit. But for any exponential growth that we're going to be doing, which is the normal one right here, m equals 0, the initial amount will always go in this spot. Kind of like, oh, hey, we saw this last year with I equals P e to the RT, but we weren't doing exponential growth and decay like viruses and bacteria and radioactive substances decaying. We were doing, what's I equals P times e to the RT? Money. Money. And this would be the principal amount or the beginning amount. Anyway, initial comes from C, but hold on, we're not done yet. Don't we need to also find K? He's a constant also, so then we would go ahead and say, all right, I also know that 1/2 is equal to, now I know that C is 4, e to the k times. Let me interpret this for you. Couldn't this be after 5 years pass, the amount of whatever we have has now gone down to 1/2 from 4? Are there substances that decay over time?
Yeah.
Yep. Carbon dating. Anyway, so after 5 years, that's the time. The amount is 1/2. It started at 4, and we're solving for k. All we got to do is what? Divide by 4? That's going to be 1/8 e to the 5k. How do I get rid of e? ln. ln. The e is now canceled out. And how do I get to k?
Divide by 5.
Wait, so what's stopping you from plugging in 0, 4 to 5k also with the initial position?
If we plug in 0, 4 right here instead of the 5, 1/2, the problem is 0, 4 will equal 4, which is true, but the k can't. Yeah, the 0 doesn't help me with the k. So those of you guys with the whole half-life doubling thing, we're getting closer and closer to why you memorize that ln formula for the constant, depending on the situation that you were talking about. But this one, 5 years wasn't the half-life. 5 years was the quarter life, technically? Nope, not even the quarter life. The eighth life? Oh, the eighth. Interesting. Right? Didn't 4 get cut into a half? A half of 4 is 2, and a half of 2 is 1, so that's a half of a half, which is a fourth, and then a half of 1 is a half. It got cut into an eighth. Anyway, this, kiddos. Oh, why are those so close together? That's awkward. Let me space them out nicer.
If it's number 44, we're going to go at it.
I don't know why it's spaced so weird. Let me move them over.
Was there a rubber card in? Wait, is that?
Section 5.1 for slope fields?
Yeah.
No.
Because it was.
There was a box, and remember the box was like a huge long paragraph that I'm like, I really don't want you guys to memorize. It's good, and I think you should highlight it in your notes, and hence why I put the box around it. I think it's good. You just don't need to have it memorized for the AP. Now guys, guess what's going on here? Same thing. It's good. In a college calculus class, you probably should, if you were making your own forevers, add it in, because it will be important. But it's not exactly on the AP. In some ways, it's there, but it's not explicitly. You're not going to necessarily see a chemistry problem, or not a chemistry problem, but a super specific application like we're about to see where you would want to memorize this. But in another calculus class, in a college calculus class, I would still highlight it, because for the test, it's going to be helpful to know. But I don't want you to put it in your forevers, because that's what you're going to be polishing, memorizing, mastering for the AP exam, and you don't need to know this for the AP exam. Not at least in a memorized fashion. You need to be able to take a differential equation and integrate it, yes, but you don't necessarily need to memorize this. So just like the slope fields, I am not making this a forever card. It is not specifically something to memorize for the AP. But in any college calculus class, it would be good to memorize. So I would highlight it, and for the test, it will be good to have, and for the homework, it will be good to have. The ratio of final with initial amounts, if they were to give us something like, it doubles something like the half-life, something like 20% remained, then we wouldn't necessarily want to keep this equation the way it is. We'd also want to think about, hey, we can also or always take any sort of percentage remaining. It depends on whether you would use growth or decay as to whether the percentage remaining was, or the amount remaining was greater or less than whether there was growth or decay. This is a way of thinking about a percentage remaining. And remaining automatically kind of denotes decay, but I mean, if it says it doubles or it triples or it quadruples, like, oh, okay, 200%, 300%, 400%, you could still think of it that way as far as what's there after time has passed. We could say, if it helps a little bit, we could say percentage present. However, guys, you see a fraction, right? So that means, I don't mean the whole number percent, I mean the decimal, right? Does that make sense? So then if it was like a half-life, then the percentage remaining would be a half or 0.5, right? 50% would be 0.5 or 1/2. If it was tripling, then it'd be 300% or just 3.00. Okay, with doubling, we can say that y of t over y sub naught is equal to 2. The percentage remaining is 200%. or the ratio would be 2. For half-life, we could say, these are just common ones that you see in chem, and half-life would be 1/2. I would assume in like microbiology and stuff too, but anyway. Half-life, the ratio remaining would be 1/2, or you could say 0.5, which would be 50%, right? And we'll use those ideas also in just a second. But sometimes they give you enough information that you're going to want to, oh, hey, we should probably label a few other things, like y sub 0. It's in the C spot. You guys remember what y sub 0 or what C represented?
Initial.
The initial amount. Or it could be the initial population, depending on what you're talking about. The initial amount, the initial population. And E, not E, sorry, E is a constant. T is time as in the number of years or minutes or seconds that are passing. But the only other one would be K. K would just be the rate of change in some senses. The rate of change in some senses. Think if you take the derivative, you're going to have times U prime or times K. So when t equals 0, everything cancels out to 1, and then you just have the k remaining with the initial. So k would be the rate of change. Okay, but once again, am I making this a forever card? The answer is no. Okay, but let's use it. Let's see how we do. Let's use it and see how we do. Ooh, go team. What do you guys see? As you guys are reading, I'm just going to give you a hint for what this wording is talking about. Talking about making an initial value problem, what they're saying is, hey, give us a problem that if you solve it, you will get y of t with the c plugged in. So the question is, first of all, guys, is this growth or is it decay?
Growth.
Which is why I put positive ky, not negative ky, right? So if you were given y prime or dy dt is equal to positive ky, and if you were given, ooh, okay, so hold on, is equal to ky. What's my such that? My initial condition. Remember, we always need a point to solve for c. When time is 0, population is, okay. They could give you this and say solve, and you're going to end up with what you're about to see. That's what this question is saying. Set up what problem could be given mathematically that's in words. What could be given to you in order to solve with calculus, which would lead you to the solution to this problem? So, if it was a calculus problem, no word problem, they could just say like, hey, solve this differential equation when you have the point. But what could it apply to? Oh, an initial population of bacteria growing exponentially at a rate of 2% per hour. Ooh, 2% per hour. Wait a minute. Hold on. We can plug in something else. What else can we plug in, cool kids? The rate. 2 per hour. So they could give that to you. If there were no words, they could just give that to you and say, solve the math problem, please. But really, it's in context of what's going on up here. Does that kind of make sense how the words can go into? So if we know that that's the initial value problem, then how are we going to actually solve for y of t? Same problem, we're just on to letter B. Well, we could go ahead and take that y prime, see it as dy dt. We could multiply the dt on the other side with the 0.02. We could divide by the y, but hold on, guys, didn't we already realize what happens every time? We're going to end up with, and here's where the little forever card comes in handy. The AP doesn't ever make you go from here to here in a memorized fashion. They're going to actually make the differential equation a little bit harder, so you could jump here. So that's why I'm not having you memorize it. But in homework, you can jump and say, wait a minute, I know who that's going to be. That's going to end up being y sub naught, aka 10,000, times e to the k, which is 0.02 t. Exponential growth is so common, they don't necessarily need to memorize. No, sorry, you don't necessarily need to integrate every single time to get there. But once again, the AP is going to give you a harder differential equation that you have to show your skills, and you won't be able just to jump to the memorized answer. So hence why it's helpful in general, but not specifically for the AP. Do we have a formula for y of t? Yep. You guys see where the 10,000 came from? Uh-huh. Do you see where the 2% came from? Okay, what else could they ask us to do once we get there? How long does it take for the initial population of bacteria to double? There are a few ways of doing this. The next part says, how long till it doubles? Yeah, one way is to think mathematically. Well, if it doubles, I know it started at 10,000, so it must become 20,000. And 20,000 is the new population that goes in the y spot at a time t. But some of you might also have looked in that little box and said, wait a minute, percentage remaining. What could I say is the percentage remaining, or the ratio if it doubles?
2.
I could just say 2 equals e to the 0.02 t. I didn't even need to know it started at 10,000. I could just say the ratio is 2. Is that what you said first? 2 ln of 2 equals t. Chem people, do you remember anything to do with ln of 2? Here's why. Dun, 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 dun. Now, if it was like a multiple choice, would we get a decimal? Yes. Pause. Uh-oh, hold on. If it's a long answer, we can't just get a number. We also need to put a unit. So we'd also have to put hours. Does that make sense? Well, I think you guys did ln of 2 over 0.02. I might be wrong. Over 0.02. Doubling always has ln of 2, and half-life always has ln of 1/2. What's different? What's new? In letter C, we could have just said, hey, the ratio is 2 and gone from there, right? Which we kind of, in a sense. But this one, is that an easy ratio? No. So then if Tyler hadn't given his idea, this one, we wouldn't have thought of the easy ratio being, 2. And no, we're just going to actually set the 45,000 on the left. But since Tyler did the other one the way he did, really this is just like inventing the wheel. We already talked about it, yeah? Well, what's going to change? We're going to divide. Isn't it going to be 4.5?
Yes.
So we're going to have 4.5 is equal to e to the 0.02 t.
So it's basically...
Do you see anything in common from the last?
It's the same setup.
It's the same setup. You have 1 over the rate of change times ln of the ratio of what you have from what you started with. Once again, they give you a harder differential equation so that you can't just use the memorized tricks. Hence why, good try. Does that kind of make sense though, guys, what we're doing? Okay. What about this guy? Ooh. E. coli. E. coli. Very different. Eat one and avoid the other. Anyway, E. coli. E. coli doubles every 20 minutes.
Do we take T with respect to minutes? Or?
Yes. T with respect to minutes. Doubles. Okay, remember, what would the math problem look like, even though the science is saying this, what would the math problem look like if they wanted you to solve for y of t?
We have to do y prime.
Yeah, y prime.
Kt
ky. Yeah, because it's the rate is directly proportional to the amount. The rate directly proportional to the amount.
With an initial part.
With an initial of
Something.
uh,
We'll figure that out as we go along.
right now the math problem is kind of lacking, right? Kind of like, what's k? A number. What's my initial value? We'll come back to this in a second. Maybe we didn't have enough information to go straight there. I'm not saying you can't find it, but you know what? We're going to have to find it when we get y of t. So, okay, fine. We know, according to our math, we would have kept the k in there and been like, I don't know. Then we would have kept the c in there and would have been like, I don't know. Okay. We would have ended up, after integrating, at, this is growth again, right, guys? Okay, what do we know? We're not sure that, and we're not sure that, but what do we know?
Well, no, the final is going to be
If it's
and then to get
can't I say 2 is equal to, remember, we don't need to know the beginning and the end, we just need to know the ratio. What's the ratio for doubling? 2 equals e to the k times, we can find k. Because they told us the ratio is going to be 2 when time is 20. Sweet. So then solve for k by taking ln of both sides. Hey, doubling. There it is again. 1 over 20.
And now we can solve for the initial.
And now we can solve for the initial because, can we?
No, because we still need an initial amount.
Yeah, no, it's still dependent on what your initial amount is.
Yeah.
So we can do our
Because we can't just plug in time as 0.
1 over 20 ln of 2 times t, right? We can do that.
Because if we plug in 0,
This k might make a little more sense now because it's 1 over t times ln of 2, the doubling over the time it takes to double. That might make a little more sense. Now, I shortened the problem when I wrote this. I shortened the problem just a little bit. It technically said a single E. coli. So what can I say?
So you can also say that there was an initial.
Yeah. Otherwise, would we know? No. But a single E. coli, like, oh, I realized that, I don't know, a year or two after I did it. I was like, oh, okay, well, dun, 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 dun. Sean, did that answer your question?
Yeah.
Otherwise, we'd be a little stuck, yeah? Phew. How many cells are present after 2 hours? Can't I just do y of...
Just y of 2.
No!
No, wait.
Just 120.
Yeah, got to make sure dimensional analysis, our units are matching. But now I can go ahead and do my 1, which is just e. And then I have my 1 over the time it takes to double ln of 2. Yes, people in Chem would probably just multiply 1 over the time to double times ln of 2, but I know where it came from now. Wait, hold on. T is who?
120.
Got it. You guys want to see how to solve this without a calculator? It's 120 over 26. Can't I bring 6 up to be a power? Can't I cancel out? Hey, if it doubles every 20 minutes, doesn't that mean in 2 hours it's going to double, 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 double 6 times? Oh, good team. So therefore we have, let's see, 2 cubed is 8, and 8 and 8 is 64. Dun, 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 dun. You guys follow my mental math, right?
Yes.
2 cubed times 2 cubed. Pre-cals would be like, oh, be all impressed. You guys are like, meh. Okay, now what?
So you just do 1,000,000 equals 1 e to the
Constant times time.
we find k.
Because we've been using the doubling constant. We've been using the doubling. The 1, ln of 2. So now we can just natural log both sides.
Mm-hmm.
And we can divide by the entirety, because that's technically a constant. 1 over 20 times natural log of 2.
You guys just plug and chug that, right? But it might be nicer to do.
Yeah.
20 minutes. If they wanted hours, what would we do? Divide by 60. Could you also have made 20 minutes 1/3 hour to begin with?
Yeah.
Yeah, but who wants to do that? Ooh, polonium.
210.
With a half-life of 140 days. What would change is that now you have y prime equals negative ky with an initial condition 10. That's what the math problem could look like. But long story short, if they wanted to solve for y of t, couldn't we just say, oh, hey, no big deal. We know what's going to happen because polonium decays exponentially. So therefore, start with my initial amount, e to the negative k t.
And then we have our inputs.
We have our clue. 1/2, which I could put a 5 and then divide by 10, whatever. 1/2 is going to equal e to the negative k times how many days? Which, can we kind of say we know what the math is going to do? And it's going to be ln of 1/2, pause, equals k. Does that make sense? Go team. And for some of you in chem, you were like, wait a minute, I don't remember ln of 1/2. Wouldn't the negative just go up and be a power, and it would be ln of 2, 1 over time? Dun, dun, dun. ln of 2, it was pretty important in chem. Bye, cool kids. This homework due on Monday.
Find the formula for y of t, you just plug in the k.
Yeah.
Oh my gosh, dude.
Dun, dun, dun.
Time to go back and watch the video again.
Yeah.